I'm going to talk about different types of crystalline solids now that we've talked about how different arrangements of particles in crystalline solids. The flow chart kind of breaks it down for us here. Crystalline solids, they can be molecular, ionic, or atomic, and that's depending on what the particles are, whether they're molecules, ions, or atoms. Atomic solids can be broken down into how they are connected to each other, what holds them together. Non-bonding atomic solids just held together by dispersion forces because that's the only intermolecular force that an atom has. Metallic atomic solids would be metals held together by metallic bonds. And then we can have network covalent solids. These are very interesting solids. These are atomic in that they don't have molecules, but the atoms are all covalently bonded to each other. So in a sense, a piece of like this quartz is one ginormous molecule because they're all covalently bonded together. So molecular solids, of course, have molecules, and those molecules are held together by intermolecular forces. It could be dispersion forces, hydrogen bonding, dipole-dipole forces, etc. Because intermolecular forces are relatively weak, these solids tend to have low to moderately low melting points. And there's a couple of examples there. How the molecules in a molecular solid are arranged can vary. So a given solid can have more than one form. So when a molecular solid crystallizes in different structures, those different structures are called polymorphs, different shapes, many shapes. And those polymorphs can have different properties. An interesting example of this is chocolate. So when you make chocolate, the part that makes it chocolate is the cocoa butter. And depending on how you heat and cool the cocoa butter, you can end up with different crystalline structure. It's a little hard to see there on the screen, but this piece of chocolate has sort of a light-colored, messy-looking surface, right? And you've maybe seen that when you open a chocolate bar that's been sitting in the cupboard for a while. That's called bloom. It's not harmful or anything, but it's not very attractive. This piece of chocolate is nice and smooth. So this table gives different crystalline types, different polymorphs of chocolate. And they have different melting points, and they have different physical characteristics. The ideal one is this number 5. This has a melting point that is high enough that it won't melt in your hands, but low enough that it will melt in your mouth. So that's nice. It's firm, has a nice snap, it's smooth and shiny. It's just really nice chocolate. Now, chocolate made in a different way can have a much lower melting point, and so then you pick up the chocolate bar and just the heat from your hands causes it to begin melting. Maybe soft and crumbly instead of nice and firm, etc. And that has to do with how the solid was allowed to form different crystalline structures for cocoa butter. Ionic solids, of course, are held together by ionic bonds, and so these generally have very high melting points, and we're going to talk about these in another section. In the atomic solids, the non-bonding atomic solids are just held together by dispersion forces. These will form closest packed structures to maximize the coordination number, minimize the distance between the atoms. These are going to have extremely low melting points. The only examples of non-bonding atomic solids are noble gases in their solid form. And here's xenon, the largest noble gas, melts at minus 112 degrees Celsius. That's a low melting point, right? I would qualify that as extremely low. Metallic atomic solids, this would be all the metals, okay? And only the metals. So these are held together by metallic bonds. Here we have a picture of the electron C model where valence electrons are sort of pooled among all the different atoms, and this is what allows conductivity of electricity and heat. These are also going to form closest packed structures. The forces of attraction here are non-directional, and so they're just going to get in as close as they can to lower their potential energy. The melting points here vary widely. We know that mercury is a liquid at room temperature, but many metals melt at extremely high temperatures, and so it's just kind of all over the place. Gallium's kind of neat because it's a solid at room temperature, but it'll melt in your hand.
This is Kate. For the melting points, does that have to do with the intermolecular forces that they have?
Well, metallic solids technically don't have intermolecular forces. They have this metallic bond. And so there's not really any good trends or patterns I can tell you about.
So it's just depending on how they're packaging and stuff? The bonds?
Yeah, it's complicated. It's complicated. Yeah. Network covalent atomic solids. Here we have atoms held together by covalent bonds. Here the crystalline structures are generally not closest packed because those bonds happen at certain angles. So we just got done talking about valence bond theory and hybridization of atomic orbitals. So if you have a carbon atom and it's going to bond to other atoms, it's probably going to be sp3 hybridized and form 4 bonds, and those bonds are going to be arranged tetrahedrally around the carbon atom. And so you're not going to be able to pack things in that violate that tetrahedral orientation. So the crystal structure is largely determined by the geometry of the covalent bonds. Network covalent atomic solids have very high melting points because they're held together by covalent bonds, which are much stronger than hydrogen bonding, the strongest intermolecular force. So we should be able to look at the formula for a solid and identify what kind of solid it is. This actually is not difficult, provided you don't overthink. Okay? So what kind of an atomic solid is AU? Metallic. It's a metal, right? So it's a metallic atomic solid. So this would be metallic. Now, if it didn't tell you atomic, if it just said what type of solid, well, AU, you don't have ions there, you don't have molecules, so it kind of has to be an atomic solid, right? A question like this: which solid would you expect to have the highest melting point? Well, what kind of solids are these? MgO. Yeah, that's ionic. A metal, nonmetal, that's going to be an ionic solid. What about this one, I2? That's a molecule, right? This is a molecular solid. And krypton there? Is krypton a metal? It's a nonmetal. Is it ionic, molecular, or atomic? Atomic, right? There aren't any bonds here. It's just atoms. So then what we need to think about is what is holding these together? Well, we'll start at the bottom. For krypton, it's an atomic solid. What's holding the krypton atoms together in a solid form? Just nothing? Dispersion forces, right? So this is an example of a non-bonding atomic solid. We would expect this to have an extremely low melting point. For this one, we can be helped out by the periodic table. We can look at the color of the element symbol. It's a gas at room temperature, right? So that's probably not the highest melting point. I2. So this is a molecular solid, has individual molecules. How are the molecules held together? Dispersion forces. This is a nonpolar molecule. It's just going to be held together by dispersion forces. And then we have this ionic solid, and what's holding that together? Ionic bonds, right? In an ionic compound, you've got magnesium ions and oxide ions, and they're going to form some sort of a lattice, and they're all going to be attracted to each other. And so you have ionic bonds, the force of attraction between these going in all directions. Ionic bonds are very strong. So which one do you think has the highest melting point? A, yeah, magnesium ions.
Because it's the ionic that it's in the intermolecular forces that is one of the strongest.
Well, technically, ionic bonds are not intermolecular forces. There's the ion dipole force, which is considered the strongest, but this is an ionic bond, which is just in another class. Ionic bonds and covalent bonds are way stronger than those intermolecular forces.
So just like, when it comes down to it, what is stronger, ionic or covalent bonds?
That's a good question. Which is stronger, ionic or covalent?
In chemistry, they always say like ionic, but then in like micro, they always say covalent. And so it's kind of confusing.
It's complicated?
Yeah.
Yeah, it really depends. And it kind of depends on what sort of strength you're talking about also. If you're talking about something melting, I would bet on the ionic substance as having a higher melting point. If you're talking about, well, what's easier to break physically, I'd say the ionic bond might be easier to break. If you hit an ionic solid with a hammer, it's going to shatter and just, break into pieces, whereas a molecular substance probably is not going to do that. You can't smash a molecule apart.
Kind of depends what you're measuring.
So it depends on what sort of strength you're talking about. But they are both much, much stronger than intermolecular forces.
Okay. Thank you.
Yeah. So if you see a question like this on an exam, don't freak out. Just think about, well, what do I know about these things? What's holding them together? What's stronger? What's weaker? Now here between I2 and krypton, if we were trying to figure out which between those two has a higher melting point, I would say I would not expect you guys to be able to do that, because they both are held together by dispersion forces. You could go based on molar mass. That's about the only thing you could do, which would not give you the correct answer, because krypton has a lower melting point than iodine.
Oh.
Yeah.
Oh my god.
Yeah, iodine is a solid at room temperature,
Oh, that's right.
and krypton's a gas.
Yeah.
Yeah. So.